Welcome back to the end of the week, right? And so if you're interested, I do have the exams with me. They're in alphabetical order so I can find them. We may finish up a little early today. Content's not too deep. It's just an introduction to logarithms. And then next Tuesday we go into logarithmic properties from here. So if you want to, once we finish up, you can take a look at the multiple choice part. Again, you do have in Canvas I uploaded the other part, and I'd be happy to go over anything. All right. Because in this class the final is comprehensive, so you do want to learn whatever we had from there. All right. So, any questions before we get started? Yes, sir.
Do you know I can find a Band-Aid?
I don't.
I have this wound on my knee from falling on one of the cracks outside.
Oh no. Maybe the bookstore, which is not too far from here. I think if you go out and across, they should have something for you. If you need to, or a restroom outside, you could at least use some tissue paper maybe on it. Or, yeah, okay.
So I just have to test it.
Yeah, sorry. I don't. Anyone have a bandage with them? Sometimes I carry with them but I don't today. Okay. So, we're going to talk about logarithmic functions. These are the inverse of exponential functions. And so we're going to spend a little bit of time talking about inverse functions to kind of get us started. So what does an inverse math operation look like? So first, what does an inverse do just in life? If I dig a hole, what would be the inverse? Fill up the hole. So it undoes whatever it is. If I am writing a paper and I accidentally delete something I didn't want deleted, we now have something called undelete, and I can bring it back, which it used to be when they first had word processors. When you deleted something, it was gone. Now they've got undelete, or cut and copy, all those kind of things. So what I want you to think about is go back to when you were first learning arithmetic, addition, subtraction, multiplication, division. So early on, at some point in our lives, we learned that 3 plus 4 equals 7. Okay, you remember too. Okay, good. 3 plus 4 is 7. The thing is we usually got these facts, if we tried to memorize them, maybe we had flashcards or whatever we did, we would usually see 3 plus 4 on one side of the flashcard and 7 on the other, right? That was the answer. So we sort of broke it up that 3 plus 4 was one thing and 7 was another thing. What I want you to do now is I want you to look at this, that the three things are connected. They really should be on the same side of it. So 3 plus 4 equals 7. And then what you want to connect it with is, and again, we learned addition first, and then maybe somewhere down the line we learned takeaway. And what's addition is I've got 3 here, 4 here, I put them in the same hand. Subtraction is I've got them in the same hand and I put them into separate groups, really is what ends up happening. And so when we learned subtraction, how is subtraction connected to addition? Well, it starts with sort of what was the answer, 7, and we subtract one of the others from the other side, and that gave us the other piece. So if we see these things as 3 connected things, 3 plus 4 equals 7, then when we got to subtraction, it was 7 minus, did I put 4, equals 3. So notice there was 2 things on one side, the 3 and 4, equals a 7. For the inverse function, the thing that was alone now has a partner, and the thing that had a partner is now alone. So there's going to be one side that splits off. So I want you to sort of see this as that we're doing math by sort of rearranging things, because that's when we get to, you're going to see how that works with logarithms. That's really what we're doing. So we can go back and forth on this. And again, we could use it to solve an equation. So if I had 3 plus x equals 10, how would I go about solving this? Well, I know opposite of addition is subtraction. So if I did 10 minus 3, I could figure out what x is, right? So that's exactly what we're going to do. But when I do it this way, I call this the dance. It's a mathematical, I'm just rearranging the symbols, right? Over on this side, 3 and x were together. They separated. And the 10 that was by itself now has a 3, but the opposite operation. And so we could see it needs to be 7, and if you think 3 plus 7 is 10, exactly. What about it multiplication? 3 times 4 equals 12. And what would the corresponding inverse operation look like? 12 divided by 3 equals 4. Or 12 divided by 4 equals 3. So we would, and some of us, as we learned those inverse, division, we actually thought about multiplication, and then we would switch it around, So I can't remember what 12 divided by 3 is, but I know 3 times 4 is 12, so that must be the answer. So it's, we go back and forth on that thinking. You're going to find when we get into logarithms, that's going to be helpful thinking, because you're going to be thinking of exponentials to come back to it. Okay, so again, I call this just sort of the dance. 2 things were together, 1 thing was by itself. In the inverse, things changed. 3 jumped over from the other side, or the 12, yeah, so it goes that way. So let's get to where, let's see, or do I, yeah, I've got, well, let me introduce logarithms as sort of a log dance. Okay, so let's take an exponential, because a logarithm is an invented function to be the inverse of exponents, right? Because we learned addition, and then we found that subtraction was the inverse. We learned multiplication, division was the inverse, so we could undo it. We learned about exponentials at some point in our career. A lot of us maybe never learned about what a logarithm is because we never used it or needed it. Now we need it. It's the inverse of exponentials. So let me do this. I'll do, how about 3 to the 4th power? Can anyone help me out what that would calculate to? 3 times 3 times 3 times 3. 3 times 3 is 9. Close. Got the 1 part right. 3 times 9 is 27. 3 times 27 is 81. Or actually, I do 9 times 9. So 3 times 3 is 9. 3 times 3 is 9. 9 times 9 is 81. So yes. Okay. So what would the inverse function look like? So we've got 3 and 4 on one side. We've got 81 on the other side. So somehow 81 is going to be paired with one of the others, right? But unlike addition and multiplication, which are commutative, we could do it in the order. Can we do this? Can we take 3 to the 4th? Is that going to be the same as 4 to the 3rd? No, it's not. You don't have to even go to, it's 64? Maybe. Anyway, it's something else. It's not the same thing. So it's not commutative, so I got to be careful about what goes where. And so I think we talked a little bit about exponentials, that we give some labels here. So the 3, we call that the base. The 4, we call that the exponent or the power. And so they have their functions. What we're going to do is, when they invented the inverse function, they called it a logarithm and they abbreviated log. where they're going to put the base is that because each exponential function has its own logarithmic function. Okay, so the base goes here. And then, so since the base is on that side, the 3 is on that side, what do we got to do with the 4? It's got to go to the other side, right? Because that's what happens with an inverse. The two numbers that were together are now on opposite sides. That's just part of the dance, right? So we know the 4 has to be over here. Well, what happens to the 81? It either goes with the 4 or the 3, and this is where it goes. Okay, so you see how we're just building on this concept of an inverse function. 3 plus 4 equals 7, and then 7 minus 3 equals 4. So it's a dance. We're reorganizing it, but that's how a logarithm works. So a logarithm will have a base down here, so the log of 3, and what do you notice about this answer? Where did the answer, if we think of it as an answer because it's by itself, right? Where did that come from? It came from the exponent. So what you're going to see is the answer to every logarithm question is what is the exponent that goes on the base that gives us that answer. See, it's and if you think of this, it's take 3 to the 4th power, we're going to get 81, right? So it's kind of backwards. So if we take the log base 3 of 81, we get back to 4. The thing is we don't really know the process. It just, in fact, if you look, I used to have one from like the Civil War era, 1865. I found this old math book. They had a book. It was pages and pages of logarithms. It was logarithm tables. That's how they used to do it. They would look it up because there's probably some process to calculating it, but it's not like addition where we can take 3 and 4 and we can count and get 7. It's not like 3 times 4 and we can kind of 3 times 4 make a little grid and that gives us 12, or repeated counting. The way of getting the logarithm is we have to think backwards to exponentials. Okay. So let me show you how this works, though. What if I had 3 to the x power equals 27? What do we get? Good. So we get log base 3. 27 is going to come here and join the 3, and the exponent's going to be on the other side. We just solved for x. It didn't feel mathy. It felt more like a dance, didn't it? We just sort of, okay, these guys, I'm just going to reorganize it based on what inverses do. So this is what I call is the log dance, is how we go about solving logarithmic equations in the most part. Okay. So we can solve an exponential by turning it to a logarithm. If we were to have a key on our calculator, which we do, and I'll show you those, we could now actually calculate what's needed. And you'd see, yeah, 3 to the 3rd power gives us 27. So again, you could do this sort of backwards thinking of what power should I put here to get 27? Well, 3 times 3 is 9, times 3 more, that gives me 27. And so you could figure it out. But you could also go to a calculator. And while we're here, why don't we go there? Because, again, today's is mostly about properties of exponentials, and this is one of the big properties, is this what I call the log dance. You won't see it in any book, at least I don't think so, because I just made it up because it seemed to make sense. Maybe somebody else has stole it and written it in a book or something, but the log dance. Watch, I'm going to put log base 3 of 27 into my calculator. So let's go second quit, back to the main screen. I'm going to clear it out. We'll talk. There's 2 logarithm buttons on here. We'll talk a little bit more about those later. But if I want log base 3, where I have to go is I have to hit the math key, and then I arrow down. I keep going, and there's going to be this thing called Logbase. And when I hit enter, it gives me the logarithm. I can put the base on it. I'll put the 3, and then I can put the number in here. And instead of having to go to a table to look it up, I hit enter, and it tells me the answer is 3. 3 to the third power is 27. Okay, that one wasn't too bad, but what if it was, 28 or something? So this gives me the ability to calculate anything I need to. Okay, so we're actually getting a way to solve exponentials now, whereas after last class, all we were able to do with them is graph them and find the intersection, right? Graph the exponential, graph what it was equal to, and then find it graphically. Now we've got a way that we could actually solve those equations. Okay, and we've got a feature here. Now, if you've got an older version of the TI-84, you might not have that log basis. It came along later. If you have a TI-83, I don't think they have it, but it's in this one. Casio, they might have a similar thing. We'll show you how to do it, but if you don't have this feature in yours, we'll get you. We'll figure out how to. There's a couple different ways to do it. Okay. So, and again, we could go both ways. If I have a logarithm, say a base 7 of x equals 5, can I do the log dance in reverse and come up with the exponential? I certainly can, and that's how I solve for x, right? What is the base? 7 is the base. What is the exponent? The answer is the exponent. And then the leftover thing is here. I just solve for x. And I could take 7 to the 5th power. I'm going to get some big number. I'm not even interested in what it is. But I could do that, right? I could take 7, and I've solved. So we're going to do this log dance both ways. I guess you could call it the exponential dance. But we go back and forth, and that's how we can solve for x. Now, there's also other methods they'll show, like taking the logarithm of both sides or something. I just say do the log dance, and today we're going to do it a few times. I think it's a lot easier to deal with. But you're going to see that allows us actually to solve exponential functions, and the reverse allows us to solve logarithmic functions. So we talked about inverses, right? I dig a hole, the inverse is fill up the hole. Now, when you dig a hole and you fill it up, I don't know, every time I've done that, it's not the same as before because you've disturbed the dirt. But the idea is that you got back to where you started, right? Again, rarely you take something out of a box, you can never get it all back in something, But the idea with an inverse is that if you do an inverse and then you undo that inverse, you're back to where you started, right? So the idea is if I take 3 and I add 4, I get somewhere. And then if I subtract 4, wait, not 12. I was multiplying when I should have been adding. Let's get back here. That's okay. I got 7, and then if I subtract 4, I got back. So I took 3, added 4, got to 7. Take 7 minus 4, got back to 3. Okay, so that's the idea of an inverse. What it looks like, since logarithms are the inverse of exponentials, if I take the log, let's say base 5, of 5 to the 7th power, well, what's really going on here? Taking 5 to the 7th power, the logarithm is the inverse of doing that. So what do I end up with? Good, I end up with 7. So this is this logarithm base 5 is the inverse of the 5 to some power. So it's like, yeah, the exponent is the answer. We're going to see, we'll have a couple different ways. So good, you called it right. It was either 5 or 7, but 7's the one it is, so 5. It could also appear, I could do 5 raised to the log base 5 of 7, and notice this 5, these are inverses, so where am I starting? I'm starting with 7. I'm ending at 7. So I did something to it and I undid it. So that's the way to think of it is, yeah, I take 7 and I raise it, that's the exponent, that's the input, and then I undo it. So both of these, the answer ends up. So you're going to see some in the homework where you've got a logarithm with an exponential inside it, and they're going to kind of undo each other. You're also going to see exponents with logarithms up there. They're going to undo each other, and it's that process. So don't think too much about the math that you have to do. It's just that when they're inverses, they undo each other. Okay. Now be careful. If I had 5 to some power and then I've got a log base 3, is that going to work? No. They're not so I don't know what that is. I have to go figure out what log base 3 of 7 is, and then I take 5 to that power. So that's a lot more work. That leaves that's too much work to do. This, I do it and I undo it. Okay, so you'll see those. You'll see some of those. That's what happens with the inverse. So we'll talk, and notice in these slides it's just kind of open pages because we're just kind of talking about. So domain and range. How do we figure out domain and range of an exponential function? Well, let's look at the graphs of an exponential function and a graph of a logarithmic function. Which base should we use? What's a good number for a base? 3. I love 3. Good. I was afraid someone was going to pick like 27. That's too big. But 3 to the x. Okay, that's what an exponential function looks like. What do you notice about the domain and range of this exponential? I think we talked about this, didn't we? What would the domain be? Good. It's going in this direction, and it's going up. But it's also going that way. What do you notice about the range? Very good. So it doesn't go below 0. There's no negative stuff there. So remember this. So this is for exponentials. Remember, a logarithm is the inverse function. So what would we expect to happen for the domain and range? Aren't they just going to switch places? And that's exactly what's going to happen. So the domain of a logarithm is the range of the exponential, 0 to infinity. So notice we cannot put negative numbers into a logarithm function. I mean, well, at least not to the result. A logarithm can't have it. And in fact, it can't even handle 0. We're going to see that. Okay, you can't put 0 into a logarithm and get an answer. But the range is going to be from the domain. It's going to be from negative infinity to infinity. Okay, so I just wanted you to kind of get a preview of that, and now let's go ahead and actually graph one. Could have done that first, but I think it's, if we can, so we'll call it g of x, right? I don't know. That's going to be equal to log base 3. Oops. Let's see, how do I do this? I think okay. With Desmos, I go to their keyboard, I ask for functions, and I think I've got log functions in here somewhere. Hopefully, here it is. So yeah, log of, we'll see there's 2 special logarithms, we'll talk about them later, but here's the log. I have to use log base 3 of x, even though it's going, and we see now this blue logarithm function. We don't see any negative x's, right? We see it coming kind of like an asymptote right up to x equals 0. So we can kind of see that domain. Yeah, it's going from, it's not equal to 0, but it goes that way and goes to infinity. We also see the range. It's shooting down to negative infinity, and it's a slow growing function, but it will get to positive infinity as well. So those domains and ranges work. And it fits, right? The other thing you see is how do we know that these two are inverse functions of each other? I'm not sure we talked about this earlier, but they're reflections around the line y equals x. And I'll do that as sort of just a dashed line. And the reason y equals x, right? What does a inverse function do? It really just switches the x and y's. And if that line y equals x, all the x's and y's are equal, 1, 1, 2, 2, 3, 3. If you switch 2, 2, can you tell which one was which? No, it's still 2, 2. So that line is a place where nothing gets, when you switch it, you can't tell. 3, 3 is still 3, 3. But every other line, like x is 1, y is 3, if you switch that, then now it's 3, 1. And that would be the inverse. So you'll see this if you look at the two graphs together. They will all, because they're inverses, they will always be reflections around that line. Does that make sense? Okay. Did we talk about that earlier when we talked about inverse functions? I don't think we did. Maybe we should have, but it wasn't a real big deal. Okay, so we've got domain and range. So just think, because of that domain, and the reason you can see with the log, let me show you this. Let me clear these out. I'm going to actually graph. And actually, if you arrow up, I think you get to Logbase a little bit faster. So I'm going to put in Logbase 3 of x, and then I'm going to graph it just like I did there. Now it looks like it just starts in the middle, but it's actually going down here. It's just the calculator's features don't work real well. But let's go to the table, and if we arrow up to 0, what happens? We get an error. You can't put a 0 into a logarithm. If we go to the negatives, you can't put negative values in. You can't take the log of negative 3, for that matter, right? Because, again, if you think backwards, what would that mean? It would mean that we could take something like 3 to some power and get a negative. We can't do that. We get close to 0, but we can't get negative. So that's what happens. And again, use your graphing calculator or Desmos or a graphing tool so that you can see a picture. You can see the tables, so the values. So analyze it by patterns. That's mathematics. We learn by looking at numerical patterns. We look at symbols and the manipulation we can do with algebra. We look at graphs. We put them all together now, and we get a much deeper understanding of what we're doing. Doing good so far? Again, this is sort of an overview of logarithms. We'll get to actually manipulating logarithms later. Oh yeah, I almost forgot about that one. And so there's actually a homework problem which asks us to find the domain and range of, or at least just the domain of this one. So what would I do to find the domain of a logarithm? I would take its input, and what does this input have to be? What's that? Thank you. It has to be some positive number. Yes, yes. It can't be 0 and it can't be negative. So good. It has to be greater than 0. But that's kind of, how do I solve that? I can't, yeah, I can multiply both sides by negative x minus 1, but then when you multiply 0, it kind of gets it out there. One of the best ways to figure out domain, let's just graph it. And the other thing is, there's no base on this thing, is there? What would its base be? Okay, you guys knew the secret. Okay, yeah, so that's one of our special ones, is when they don't have a base, it's really base 10. Just like in math, there's always something that they don't write down. So this is really base 10, but we don't need to use that because if we don't put a base, our calculators assume it's base 10. So let's go back. I'm going to graph this and I'll show you. So let's clear this stuff. Let's get rid of this stuff. So we'll put in the function log. I don't put a base, and let's put in, what was it, x plus 8 divided by x minus 1. Oops, not 10. Whoa, that's kind of funky, isn't it? And again, because this one is, as you get a certain value, you're subtracting 1. If you got a negative here, maybe you get a negative over a negative. You can actually put negative numbers in here. But what would this, let me zoom back in. What would this suggest as far as the domain? I can plug these negative values in, right? Because I see a graph there. So it looks like I can go from negative infinity. Where does it stop? Negative 8. Again, if I zoomed in a little bit, I would probably see that. But this is, because these are every 2, so at negative 8, it's sort of, that's an asymptote, right? So that's not included. So here's my domain here. And then I've got this open space where none of that stuff's in the domain. So I union it. Where does this look like it's starting?
1.
Very good. And you saw that x minus 1, so you could kind of solve for it. Starts at 1, and then it looks like it's going to go till positive infinity. And so that would be my domain. Yes, sir.
Why can't it be log base 10 of negative 8? Because like x minus 8 or x plus 8 over x minus 1 wouldn't divide out to be negative 8.
Negative 8. Well, no, if you put in negative 8, negative 8 plus 8 is 0. And that's in the numerator, so then you've got the logarithm of 0, and you can't, logs can't do 0. Does that make sense? So yeah, you could see why it wouldn't be 1, because you get division by 0, but if you plug in 8, or negative 8, you end up with 0 over negative 9, but that's still 0, and so you would end up with the log of 0, which is undefined.
Well, what I meant like was the x's cancel.
No, oh, the x's don't cancel.
Okay.
Yeah, because they're being added and subtracted, so you can't just cancel the x's.
Okay.
Good, good. But a lot of people think so you're not the only one, so I'm glad you brought that up, is when we're adding or subtracting things, the only time we can cancel in a fraction is we've got multiplication. But I see it in my calculus classes. Oh, let's just cancel those out. Be kind of like a nice world if it did, but it doesn't work. Okay, so sometimes, and this one I took from the homework, so you're going to see this one again in the homework, and I was thinking, how do I show that? Because it's kind of going to be complicated. It's going to have to look at a couple different things. Easy, just graph it, and it was like, okay, I see it, and then you could kind of see why each piece has to be each, and work through it. So a lot of times we can just graph these things, and we'll see it. Okay. So by graphing, yeah, we'll do it here. So we found negative infinity to negative 8, union 1 to infinity. How about the range? The range was still, and we go back to it, but it was still shooting down to negative infinity, going up to positive infinity. Guess we'll go back. The one thing I'm not certain of is whether or not it includes 0. But they didn't ask for the range, so looks like that maybe 0 is not going to work either. But x equals 0. Okay, special log forms. You guys took half my thunder away. So the two special forms are when we have log base 10 of something, we simply write it as log. We don't put the base. This is called the common logarithm. Again, base 10, because our number system's base 10, 10, 100, and so forth. So this is the common log. And you'll see that there's actually a button on your calculator, so you don't have to go into the math key and put the, it's just when you're doing the common base, common log, just you hit it. The other one is if we have log base e, and we talked about e, didn't we? The natural number. Okay, good. If you remember, it's a number close to 3. It's 2.718 something. It's but it's like it's a number like pi that never terminates. So it's always ongoing. It doesn't repeat. It's a, I think they call them transcendental numbers, but it's naturally occurring. So what they've done is they came up with a symbol ln. Some people think that looks like in, but ln of x, and they call that the natural logarithm. Or natural log. So I see the L and the N, but don't they have it backwards? Shouldn't it be natural logarithm? Shouldn't it be NL? Little history lesson. Do you know who instituted the first, or at least the modern history, first printed math textbooks? A little guy named, I shouldn't say that because he was Napoleon Bonaparte of France, the emperor. He instituted math textbooks because he wanted to standardize the teaching of math, because not only did he want to take over the world, or certainly Europe, he tried to take over Europe. His idea was that mathematics would allow him to build things that would control it. So he was highly behind all of that. So in French, anybody speak French or know a little French? I should. My mother, actually, her people were French and Indian, so she grew up. In French, it's backwards. So they say logarithm naturel. So that's why it came up with the ln, because the people who wrote the first at least the high school type math books, they were French, and so in their language, logarithm naturel. So that makes sense when you see the ln. Otherwise, I always thought it was backwards. Why do they call it the natural logarithm if they're doing ln, right? That's because it comes from the French logarithm naturel. But we'll speak English and call it the natural logarithm, or however you want to do it. Okay, but it's an ln. A lot of times when you're seeing me write it, I'll write it sort of in a script so that it's an L, because to me it does look like in or something. So I'll write a script ln. But when we're working with it, a lot of times you'll also see me rewrite it as log base e, because sometimes we need to know that base, right? Because if we're going to do the log dance, we have to know what that base is. And that's the problem we have, is when we don't have the base written. If I need to rewrite this in the other form, I just have to remember, well, that's 10 to some power equals x, right? I don't know. I would have to be equal to, so if I were to go to solve this, I say, okay, 10 to the third power equals x, but since there's no base here, I have to remember that that's a 10. When I see ln of say x equals 5, I have to remember that the ln, the natural logarithm, has a base of e, so e to the fifth power is equal to x. Okay, so I can still do the log dance with these ones, but I have to remember that the symbols we use for them don't show me what the base is. So I have to remember. And again, it's not too bad. It's only two numbers. One's 10. Okay, I got that because base 10. The other's the natural one, e, which is used a lot in finance and engineering because, again, natural processes, that number gets used a lot. But those are two special log forms. We will talk about transformations, which we just talked about on Monday, right? Shifting, left, right, up, down. So let's just kind of do this. If I had the log, and I'll just won't do a base, so we'll do base 10, right? If I do x minus 8, thinking about what the logarithm graph looks like, right? We found that it looks something like that. What will this new one look like? What does x minus 8 do to the graph? Does it move it up, down, left, right? Moves it in the positive direction. Yeah, I have to, because it's opposite. So it's going to move it 8 in the right. So it moves it, yeah, to the right, 8. So it'll look something like that. So it's just push it over. And again, you could use your graphing calculator to do these, and you'll see. But there's going to be a few ones that have some transformations of moving it. So it's just like take that graph. We're adding inside, it's going to move it that way. If I, let's see, let's take a new one. If I had log of x plus 8 this way, what's going to happen? It's going, oh, let's see up there. It's going to move it up. And so I don't, it still goes down to infinity, but it'll be like up here somewhere. It'll move it up 8. And again, it's easier, some of these, just to go ahead and graph it. Again, we're not going to have you judged off of the graphs and stuff, but in the homework, sometimes they have a tool, and so you just, regraph it. Before we get too far, there's just one thing I don't think that was in this, but it's kind of a, if we have anything to the 0 power, what do we get? 1. 27 to the 0 power gives us 1. So how does that work for a logarithm? So let's maybe take this first one. If we do the log dance on these, the base stays the base, so that's natural log. The 1's going to come over, and that's going to be equal to 0, right? Log base 27. 27 is the base, the 1 comes over, the 0 is the answer now. So notice when you put 1 into a logarithm, what are you always going to get? 0. Because when you take a 0 exponent, you're going to get 1 as your answer. Okay. So that's another little feature you'll see is for whatever, now it's not with a translation, like I could plug in 1 here and it's weird things are going on, but yes, if I plug in 1, the log of 1 is always 0, regardless of which base, because anything to the 0 power is 1. This one here? So if we think in exponents, if we have any base, any number, and we raise it to the 0 power, we always will get 1 as our answer. One way to look at that is to think, let's just stick with 27. What if I had 27 squared over 27 squared? Those are the same number. That number divided by itself is going to be 1, right? What would I do with the exponents? So another way we found is we could also think of this as 27 squared. We could subtract the exponents, right? So 27 to the 2 well, what's 27 to the 2 minus 2? That's 27 to the 0. So 27 to the 0 has to be 1 for all this to work. That's kind of how I introduce it, at least. So we find that whenever you raise something to the 0 power, you're always going to get 1. And remember, logarithms are the inverse. So whenever you plug in 1, you're going to get 0. So on the exponential, you plug in 0, you get 1. Logarithms will reverse that. The x and y will change. Does that make a little bit more sense? And it's not something that really clicked that much with me, but you'll see on when you go to graph things that whenever you know the x equals 1, if you're just doing a logarithm, it's always going to be the 0. So like that first one I drew right here. Now these have all been translated, but this point here is going to be 1 comma 0. Because that's this, when I drew this, this was log of x. Plug in 1, the y value is going to be 0. Now all these other ones I translated, so that changes it. I can move those. So this point, when I did this, this point here is now going, since I moved it over 8, right, I was at 1, 1 plus 8, this is now going to be 9, 0. So, I could kind of, so a lot of times we end up using that particular point because it works for every logarithm, 1, 0. And if we're going to translate, remember when we were translating, we focus on one point, and for us, it doesn't have a vertex really. So the place it crosses the x-axis is kind of the point we focus on when we move it. We know where that goes. So solving logarithmic equations, how are we going to do it? The log dance. Okay, it really is. And so we'll have, I think, did I put an example in here? Nope. And this is the last slide. Well, let me think of one that we had. So I think we had something like log base 4 of 2x minus 6 equals 2. So we're going to see something like this. It might be a little bit more complicated. But what would we do to solve this? Well, that x is in a lot inside. It's inside, so I got to get it out. What does the log dance give us? What is this for? What do we call that? The base. What is this 2? So on a logarithm, it's the answer, but on an exponential, it's the exponent, isn't it? So what this tells me is I can take 4 to the second power, and what's that going to equal? 2x minus 6. So I haven't quite solved it yet, but there's now no longer a logarithm. There's an exponential, but do I know what 4 to the second power is? Well, you don't know if I know, but yes, I do. It's 16, isn't it? We could figure it out. So yeah, so this is going to be 16. So notice we got it, so it's something we can all calculate. And then we just solve for x. We got a linear equation. Add 6 to both sides. 22 equals 2x. Divide by 2. x equals 11. So we solved it that way. So in the homework, they will ask you to solve a few, do the log dance step, and what you'll find is you'll always get your base to that exponent. You'll be able to plug that in a calculator or know what it is, right? It becomes a number. The inside stuff is on the other side, and then you can use linear techniques to solve. A little bit later, there could be a quadratic in there. We'll learn some other properties of logarithms that are helpful, but that's basically takes you through the homework. And that's what I did. I looked through the homework, what you're going to need to do, and I kind of got a few examples of each sort of one. We're still done early, but let me ask you one thing. This is more historical. Do you know the historical importance of logarithms? And this is not too, like, this would be like the 60s. What did they not have in the 60s that we have today? Well, there's a lot of cell phones, all that. But what else? For math class. You all have, you know how much power is in this thing? This thing used to, something of this power, like they'd have tubes in this whole, probably the first floor, to just be able to, and it still couldn't do all the things your little handheld could do. In the 60s, that's what it was. So, and engineers, you know what they were using, since we didn't have these little things. Nobody had a whole building full of with a computer in it. So they use this thing called a slide rule. Slide rules are based on logarithms, and we're going to find when we look at the properties of logarithms, that's what they really use, is that logarithms allow you to do exponential calculations by just multiplying and multiplication and addition. You have to go through a few processes to get there, so it's not like just enter the numbers in and get your answer. But with the slide rule, it uses the processes of logarithms for those folks back then to solve things. In the 60s, my dad was actually a rocket scientist. He worked on the Apollo project. He worked on the 12th chamber engine of the Apollo rocket. He's just a young guy in his 20s. But that's, and I had his slide rule for a while. I moved a couple times. I can't find it anymore. It's probably in a box somewhere. But it's kind of interesting things. So we'll get into that. We'll look at the properties of logarithms, but they are also helpful. Some people say, well, we don't need them anymore because we got these calculators, but they are, whenever we're doing an exponential process, we always need the logarithms because they will help us solve and undo it. Okay, so that's all I got for you. You got any questions before we call it a lesson? Logarithms, so these are just the properties. Okay. So I'll cut it off